June 1983. A deep rumble moves through the canyon wall at Glen Canyon Dam. Red water, loaded with chunks of concrete and raw sandstone, pours from the left spillway tunnel. The 710-foot concrete arch hasn't moved, not an inch. But something inside these tunnels is ripping itself apart, and the force behind it begins with nothing more than a collapsing bubble. I am Tom Kessler. As a hydropower enthusiast, I spend my time digging through primary sources and official investigation records to understand how these massive structures actually work and where they fail. The 1983 crisis at Glen Canyon is often misunderstood. The massive 710-foot concrete arch never moved, cracked, or shifted. The real battle was fought out of sight, hidden inside the left spillway tunnel, buried within the canyon walls, far from the main dam body. It began when operators heard a low, heavy rumbling vibrating through the rock. Suddenly, the torrent of water plunging through the mountain turned a violent, muddy red, carrying chunks of shattered concrete and raw sandstone debris out into the river. The spillway system was tearing itself apart from the inside. The emergency became a question about how our infrastructure gets tested when we least expect it. Glen Canyon Dam is a massive 710-foot concrete arch structure completed in 1966 after a decade of construction. But its location on the Colorado River presented a severe physical constraint. Tucked into a narrow vertical sandstone gorge, the canyon walls left virtually no room for a conventional open-air spillway. Engineers had to get creative. To bypass floodwaters, they bored two massive 41-foot diameter tunnels directly into the red rock of the canyon walls. To save both time and millions of dollars in excavation costs, the designers made a decision to repurpose the lower portions of the massive diversion tunnels that had kept the riverbed dry during construction. This meant the new steeply sloping spillway shafts had to drop down at a 55-degree angle and bend sharply to connect with the horizontal diversion passages. This elbow, where the path of the water abruptly flattened out, introduced a severe geometric kink. It was an elegant compromise on paper, but it created a silent vulnerability. This geometric bottleneck wasn't a complete mystery to the wider engineering community. Decades earlier, in 1941, Hoover Dam's tunnel spillways suffered massive cavitation damage during a prolonged spill. In 1967, Yellowtail Dam in Montana saw its concrete lining shredded in the exact same configuration. These precedents proved that this specific tunnel layout was highly vulnerable when pushed hard. Yet at Glen Canyon, the danger remained purely theoretical. For the first 17 years of the dam's operation, the reservoir was still filling, slowly drowning the Navajo sandstone, but never rising high enough to force a real test. The spillway tunnels sat dry and silent. It was a classic engineering trap, a known risk left completely unconfirmed in practice, allowed to sleep in the dark for nearly 2 decades while the water quietly climbed. The winter of 1982 into 1983 brought a powerful El Niño pattern that disrupted weather across the American West. In January, early forecasts by the Bureau of Reclamation did not trigger any alarms, suggesting only a normal spring runoff. Based on those projections, operators kept Lake Powell near capacity, leaving very little empty space to buffer a major flood. But then, the weather pattern shifted. Heavy, late-season snowstorms repeatedly slammed the Rocky Mountains throughout April and May, piling a massive snowpack onto the headwaters of the Colorado River. By the time the calendar turned to June, the reservoir was already 96% full. Then came a sudden, intense, warm spell. It compressed what should have been months of gradual snowmelt into just a few weeks. By June 1st, the Colorado River was surging into Lake Powell at 92,400 cubic feet per second, and that was up from less than 20,000 just a month prior. Faced with a massive volume of water that far exceeded the capacity of the power plant turbines, operators had to act. On June 2nd, they made the decision to open the left spillway gates, releasing an initial 10,000 cubic feet per second. The dam had officially entered an operating regime it was never designed to sustain. As water rushes down the 55-degree incline of the spillway tunnel, it rapidly accelerates, reaching speeds of over 100 feet per second. At these extreme velocities, the physics of flowing water change. When this high-speed torrent encounters even the smallest physical imperfection along the concrete lining, like a tiny ridge, a joint offset, or a microscopic calcite deposit, it is forced to deviate. This sudden diversion causes the water to shoot past the obstruction, creating a localized pocket of extremely low pressure directly behind it. If the velocity is high enough, the local pressure drops below the vapor pressure of the water. This drop causes the water to flash briefly into vapor, forming millions of microscopic bubbles. These bubbles do not last. As they carry downstream into zones of higher pressure, they suddenly and violently collapse. This implosion occurs with astonishing speed. The surrounding water rushes into the empty space, focusing into a microscopic but violent jet that strikes the concrete surface. The force is comparable to how a singer's voice can shatter a wine glass at the exact right pitch, using focused energy to break a solid material. At Glen Canyon, this process repeated millions of times per second. The localized pressure spikes from these implosions exceed tens of thousands of pounds per square inch, easily surpassing the strength of the concrete. Each tiny impact spalls away a minute fraction of the cement, leaving a rougher pit behind. This is where the process becomes a runaway feedback loop. Every new pit creates a larger surface imperfection, which generates even lower pressure drops, seeding more vapor bubbles and allowing the next bubble to do even more harm. The damage accelerates, turning a microscopic bubble into a hydraulic jackhammer. With the spillways failing from the inside, operators could no longer rely on them to vent the deluge. On June 5th, crews began an extraordinary field improvisation. Working through the night, workers bolted 4-foot plywood flashboards, supported by angle iron frames, directly onto the left spillway gates. This temporary barrier raised the reservoir's capacity, buying time while millions of acre-feet of water pressed against the dam. But the plywood leaked, and the water kept rising. Within days, engineers drafted designs for 8-foot steel plates. Sourced from local warehouses, these 20-ton assemblies were built and bolted to the gates by July 6th. On July 15th, Lake Powell finally crested at 3,708.34 feet. The water sat just half an inch below the top of the steel boards, mere inches from overtopping the gates. The torrent bypassed the turbines and surged into the Grand Canyon, pushing the Colorado River to nearly 100,000 cubic feet per second. These massive flows transformed the river, creating violent, towering rapids that commercial rafting guides had never seen in the post-dam era. On June 6th, a 20-person wooden commercial raft was swept up in the initial surge and flipped, throwing passengers into the freezing torrent. While downstream rescue crews recovered everyone safely, the National Park Service took the unprecedented step of closing the river to all tourist traffic on June 29th, directly halting the rafting season. Once the tunnels were drained, crews found a massive crater, 32 feet deep, cut through the concrete lining and into the sandstone beneath. How close this came to total failure remains a point of honest disagreement among engineers. Some believe the dam was never threatened, while others argue a catastrophic breach was imminent. To fix this permanently, workers retrofitted the tunnels with a small step called an aerator. This device draws air into the high-speed flow, cushioning the collapsing vapor bubbles so they lose their destructive force, a design successfully proven during an even larger flood the following year. Glen Canyon taught us the danger of letting nature test our engineering assumptions. I am Tom Kessler, and here we study these critical hydropower stories. Share your first-hand accounts or corrections in the comments, and join us next time for a dam disaster in the Italian Alps. Subscribe to the channel today.